Okay, let's continue talking about heat transfer. And as you may recall from the previous lecture, we talked about three different modes of heat transfer. One is conduction, the other is convection, and radiation. So when it comes to conduction, we use Fourier's law to model heat conduction. And Fourier's law says that the rate of heat conduction is proportional to the area times the temperature difference divided by the thickness. So the rate of heat conduction we call as Q dot, big Q dot, not to be confused with the little q. A little q dot is heat flux, okay, which is rate of heat conduction divided by area, okay? So rate of heat conduction is proportional to area times the temperature difference divided by the thickness, and the proportionality constant is K, the thermal conductivity K. So the rate of heat conduction via the rate of heat transfer via conduction is going to be equal to the thermal conductivity times the area times the temperature difference divided by the thickness, which can be put into a differential form. If you put it into delta t and delta x, and take the limit as delta x goes to 0, you will get Fourier's law, which is Q dot is equal to negative K times A dt dx. And so some important things to note about this. So unlike temperature, heat transfer has direction as well as magnitude, and thus it's a vector quantity, okay? Therefore, we must specify both the direction and magnitude in order to describe heat transfer completely at a given point. Okay, so let's take a look at this example here. If we have a wall and we cut it in half and we're looking at it from the side view, and let's say it's hot on this side and cold on this side, and the thickness is L, because there's a temperature gradient or a change in temperature, this will drive heat transfer through the wall. And again, because heat transfer is a vector, it has to have direction and magnitude. And so the direction, the convention used here is that this would be positive. So heat transfer would be 500 watts in this scenario. And if it's traveling in this direction, in the negative x direction, then the heat transfer is considered negative. So positive indicates a positive direction along the x-axis, and negative indicates negative direction on the x-axis. Okay, let's talk about steady state versus transient state heat transfer. So the term steady implies that there's no change with time at any point within the medium, while transient implies that there's variation with time, or there's a time dependence. Okay, so let's take a look at this. Let's take a look at this example down here first. This steady state example here. Say the wall at 2 p.m. the wall is 15 degrees on this side and 7 degrees on this side, has a temperature gradient, so there will be some heat transfer through this wall. And then the time, at a later time, at 5 p.m., the temperature is the same, 15 degrees on this side of the wall and 7 degrees on this side of the wall. So this is called steady state, meaning that there's no change at any point. There's no change with time at any point. Now, if you take a look at this one up here, this one's an example of transient, meaning that there's a change with time. So this is at 2 p.m. Again, this one's at 5 p.m. So at 2 p.m., there's 15 degrees Celsius outside on this side of the wall, 7 degrees Celsius on this side of the wall, driving heat transfer through the wall. But at 5 p.m., the temperature's changed. Okay, now it's 12 degrees Celsius on this side of the wall and 5 degrees Celsius on this other side of the wall. So the rate of heat transfer is not the same because the temperature gradient has changed with time. So this is the difference between steady state, which I want to note in COMSOL, they call steady state as stationary. Okay, so stationary and steady state are meaning the same thing. They don't change with time. And transient state or unsteady state means it does change with time. Okay, there's another concept that I want to introduce, and that's the concept of heat generation. Okay, so what you need to know about heat generation is that heat generation is a volumetric phenomena. Okay, that means that it occurs throughout the body of a medium. Okay, so therefore the rate of heat generation in a medium is usually specified on a per unit volume basis and is denoted by E dot, and the units are watts per meter cubed. Okay, so what does this mean? Heat generation is a volumetric phenomenon. That means it's not happening on a surface, but instead it happens throughout the whole body of the medium. Okay, and so we denote the total rate of heat generation in a given medium with a volume V as E gen, big E gen, is going to be equal to the volumetric integral times little e gen times the change in volume. And this reduces to this equation down here, where the total rate of heat generation is going to be equal to this rate of heat generation on a per unit volume basis times the volume will give the total rate of heat generation. What's important to note is that also is that when you have heat generation, remember that it's a volumetric phenomena, meaning it's not going to be a surface phenomena, but instead a body volume phenomena. All right, so let's take a look at some examples on how, well, you know what, before we take a look at some examples, let me also show you, I want to show you this as well. So heat transfer can be also multi-dimensional as well, okay? So what do I mean by that? Well, you can have heat transfer along the x-axis, you can have heat transfer along the y-axis and along the z-axis. Anywhere there's a change in temperature, so say this is a pillar, okay, and it's 80 degrees on this side of the pillar and 70 degrees on this side, that will cause heat transfer in the x direction. But let's also say that it's 80 degrees on this face, and on the other face it's 65 degrees. So there's also a temperature gradient there as well. So that'll drive a heat transfer in the y-axis as well. So this is what we call two-dimensional heat transfer in a rectangular bar. Okay, you can have so you can have multi-dimensional heat transfer as long as there are temperature gradients on the different surfaces. And you can even have three-dimensional heat transfer as well. So, all right, let's take a look at an example problem. So in this problem, it's an example of heat transfer via conduction. We have a wall that is 50 millimeters thick, and the inner and outer surface temperatures are 20 degrees Celsius and 5 degrees Celsius respectively. Okay, so there's a temperature gradient. The inner wall is hotter than the outer wall, therefore heat will be transferred through the wall. Okay, and we're asked to find the heat flux for two different types of walls that have different conductivities. One wall has a brick wall, and the other wall is wood. Okay, so let's take a look at how we would solve this and apply Foyer's law to solve this problem. Okay, so first thing, we'll draw out our problem here. So here I've drawn a wall, and here T1 is going to be the temperature inside, and T2 will be the temperature outside, and the thickness of the wall is 50 millimeters, and the coordinate system that we're using is going to be this XY coordinate system. Okay, so for the brick wall, the heat flux, okay, is, if you recall, the heat flux is rate of heat transfer divided by the area. They didn't give us any information about the area, so we can put this on a per unit basis for area. And so that's what heat flux is. It's going to be Q over A, and that'll be equal to the thermal conductivity times the temperature gradient, which is dt over dx, which can be reduced to delta t over delta x, and it can be written as negative k T2 minus T1, final minus initial, with delta x being the thickness of the wall. And so if we put the thermal conductivity for the brick, the thermal conductivity for the brick is 0.69 watts per meter Kelvin. If we put that here, again, that's going to be 0.69 watts meters per Kelvin. Times T2 minus T1. So T2 is the final temperature, which is 5 degrees Celsius, minus T1, which is 20 degrees Celsius, divided by the thickness of the wall, which is 50 times 10 to the negative 3 meters, okay, or 50 millimeters. And if you solve this, you'll get the rate of heat transfer as positive, meaning it's going in the positive direction, okay, going from hot to cold. The answer would be 207 watts per meter squared. Okay, so that's rate of heat transfer per area, which is flux. Okay, so you would get a heat flux of 207 watts per meter squared. Now for a wood wall, again, we use the same equation for heat flux, and that's equal to, again, it's going to be equal to K times delta T over delta X. So we put in K, thermal conductivity for the wood, which is 0.208, watts per meter Kelvin, multiply it times T2 minus T1 divided by the thickness, and we get 62 watts per meter squared. Okay, so a brick wall is losing heat faster than a wood wall due to the higher conductivity. Okay, so because the thermal conductivity for brick is higher than the thermal conductivity for wood, brick would have a higher rate of heat flux than wood. Okay, so that's an example of how to use Fourier's law and how to model, mathematically model rate of heat transfer via conduction.